So we will continue the discussion regarding the integration. So we had a very long holiday, so probably you have forgotten what you have learned previous week. So I'll just briefly. So we have x and y, close contour, z naught. So if fz is analytic, so this is domain T, and the domain T enclosed counter clockwise curve C, then this is the basis of Cauchy's integral theorem. That is, if we have, let me check, I wrote. We have counterclockwise curve C, then inside of this curve is called domain D, and Fc is analytic. Analytic means Fc is finite and differentiable. That means Fc satisfies Cauchy-Riemann condition, right? So in that, this integral is 0. And also we have shown that if we have a unit circle, and this is C, 1 over z dz was 2 pi I, right? That's what we have done previous week. And also c to the m dz is either 2 pi I or 0. M is -1, minus. So when m is -1, then this integral is 2 pi I, otherwise it is 0. So we have a little bit more to do. Another thing is, what if C is circle with radius R? The previous result told for the case when the radius of the circle is 1, that's called unit circle. On the other hand, we are curious whether the same formula holds if the radius of circle is R, some finite value. other than 1. So let's check. Oops. Let's call this point C as R exponential I theta, right? Then dz is R exponential I theta, d theta I. So this integral C to the dz is actually theta is 0 to 2 pi and R exponential I theta, I R exponential I theta, d theta. So this cancels out each other, this cancels each other. Again, 2 pi I, right? So actually, the formula holds no matter what the radius of the circle is. So maybe we can obtain the same thing. C to the m dz pi R to the m exponential I m theta I R exponential I theta d theta, right? So this is 2 pi R to the m plus 1 exponential I m plus 1 theta d theta. So the result should be the same. That is R to the m plus 1, 2 pi I when m is equal to minus 1, 0, m is not minus 1. So the result would be basically 2 pi I delta m minus 1, right? So delta is Kronecker delta. Delta ij is 1, 0. I equal j, I is not equal to j. It's called Kronecker delta. So actually the formula holds whether the circle is a unit circle or it is finite, other than 1. I think color is a little bit too purple, so maybe I will change. Okay, this is better. What about if the point is not the origin, but some finite point? So if we have some point z naught, and let's start with the unit circle. Then dz, z minus z naught is exponential I theta, d theta. dz is I exponential I theta d theta. Then this is C, it's a unit circle around the point z equals z naught. Then dz can be written as 2 pi exponential I theta, I exponential I theta d theta, 2 pi I, right? When C is a circle with the radius r, case this is r, then z minus z naught is r exponential I theta, right? So dz is again r exponential I theta, I d theta. C, z minus z naught, dz is again 0 to 2 pi, r exponential I theta, r exponential I theta, I d theta is 2 pi I. Right? Now if with the finite radius r, no, not z, not z. So when z 0 plus r exponential I theta. So C is a circle with radius r about around the point z equals z naught. Then we obtain the same formula, C dz, right? R m theta I r exponential I theta d theta r to the m plus 1 I exponential I m plus 1 theta d theta. Then the result will be same, right? This integral is 2 pi I when m is equal to minus 1, otherwise 0, right? So it's going to be 2 pi I times 1 So we have a general result for circle that this is probably the most general result, right? This is C, this is Z naught, this is R. Delta M minus 1, right? So far we have this formula when the curve is a circle, right? What if C is not circle? What if C is general curve? So we know that when C is circle, then we have the previous result, right? But what about this? Because the C is arbitrary. What will be the result? So in order to work out this, epsilon. This distance is epsilon. And this is Z naught. And this is rho, 0. So we deform this zero. This is C prime, C1, 0, C2. Let's say C double prime, C prime, C1 plus 0 plus C2. This is whole thing. 2, then double prime. Now, this point is outside of this circle C prime, right? C prime is composed of this C prime, C1, C0, and C2. C double prime is. Then this C naught is outside, right? So here, C naught is outside of C double prime. So this point is now outside of this circle, new circle, right? New curve, C double prime. Then the result should be, according to the Cauchy's integral theorem, this function is analytic outside, right? So it should be 0. According to integral theorem. Because Z0 is outside of the domain enclosed by C double prime, right? Can you believe this? This is 0. Because this point is now outside of this curve, right? 이 부분만 한번 해볼게요. 자, 요 점은 이렇게 정의된 커브에 밖에 있죠. 코스의 접근 정의에 의하면 이 사선으로 그어진 도메인 안에는 이 함수는 항상 원해를 되잖아요. 항상 미분할 수 있죠. 이게 미분이 안 되는 경우는 G-0분의 분수 나오는 것만 보면 묘정이 밖에 있으니까 이게 항상 원해를 하니까 0이 되겠죠. Right? You may need time to understand this particular picture, so I'll just let you take time to think about that. This is C1, right? Now we are going to magnify. So we have this following thing. C1, C2. And this is a 0. And epsilon. What happens to this C1 C2 as epsilon goes to 0? C1 is going from here to here. So let's say I'm going to put A, B, C, D. The C1 is going from A to B, right? And C2 is actually going from C to D. That means C1 and C2 in opposite direction, right? C1, C2 are in opposite directions. So what happens if epsilon is going to 0? Then C1 and C2 will cancel each other, right? Sure? Going to be 0. Can you accept this? If epsilon is going to 0, then they are going to be in one plane, and then C1 and C2 are in opposite direction. So when you do integral, which is opposite direction, you have a change of sign, right? So it becomes 0, right? And we have this point. See now. Also, this is clockwise 0. This is a unit circle. Z is Z naught plus rho exponential I theta. So 0 circle with radius rho, right? dz becomes epsilon goes to 0. Becomes closed circle, right? So when epsilon is going to 0, this 0 becomes closed, right? Right? When epsilon is going to 0, B becomes C, right? B becomes C, and therefore the 0 becomes closed. 여기도 한번 한번 해줄게요. 여기 epsilon이 0이 된다는 얘기는 B랑 C가 붙는다는 얘기지. 그러면은 이 C로도 회곡선이 되는 거지. 원이 되는 거지. 근데 이거는 클로가이스잖아. 우리가 원래 계산한 거는 카운트 클로바이즈에서 계산한 거니까 클로바이즈면은 부호가 바뀌는 거지. So it becomes minus over 0 easy. That I'm going to use a few more times, so probably you should get familiar with this trick. So I'm going to do it again. So we have now C prime C1, 0, C2. We have a Z naught. So we have the following integral. C double prime is C1 plus C2 plus 0 plus C prime. And we have the following, this integral. C double prime C minus C naught to the m dz becomes as epsilon C prime dz plus 0 right? C1 plus C2 is 0, right? And becomes actually C prime minus 0 as so if epsilon goes to 0, the C prime also becomes a closed integral, right? As C prime also becomes a closed curve. But this is circle, so and C prime becomes C, right? If epsilon goes to 0, from C and 여기도 헷갈리는 한걸로 해줄게요. 이게 붙어버리면 어떻게 돼요? C 프라임이 표공면이 되는 거죠. 그리고 C 프라임이 C랑 똑같지. 원래 C를 잘라놓은 거니까. 그죠? So it becomes C dz minus 0 equal to 0. But this is a unit and circle with a radius rho. So it becomes, this becomes what? 2 pi I delta m minus 1, right? So arbitrary curve 2 pi I delta m minus 1. This is very useful result. First, you can take a break for a few minutes. Let's continue. So we have obtained the general result that for arbitrary curve, minus 1, right? So one of the application is actually this integral. So this integral was done by Cauchy in the early 18th century. I told you that this integral was asked to solve by Cauchy from this Napoleonic War. So France has to prepare for the British invasion. So that's England and that's French. Right. So the most likely the British will land in Normandy. Right. About Normandy is probably the most proper region for the British to land their invasion force. So Napoleon knew that. Napoleonic knew that British will land at Normandy. So in order to prepare for that, the British invasion, you have to know when they will land, try to land. And usually, the timing for landing will be when the tide is low. So you need to know the time. Time when the tide is low. And by that time, because of the Newton, they knew that tide is caused by the gravitational interaction between Moon and Earth, right? So this is point A, this is point B. Then the tidal force is proportional to R1 minus R2 square. there is moon. So this is R1, this is R2, right? So R1 minus R2 square this is theta. R1 square plus R2 square minus 2R1 R2 cosine theta. And you have to take an average of this over to d theta. So that means the cosine you need to integrate this. A plus b cosine theta d theta. Nowadays, this integral can be done very easily using just numerical integration, right? Using computer. You can just numerically do some. But unfortunately, Cauchy didn't have a computer at the time, right? 200 years ago. So he has to calculate this by hand. And that's the reason why he was studying how to integrate functions to general functions and particular complex variable theory. So that's the actual history of this particular problem. So this problem has been around for over 200 years, since Napoleonic War. And motivation for this problem was to predict the tidal force, or the height of the tide, in some particular region like Normandy. So sometimes it may help to understand the problem if you know the history associated with the particular problems. But now we can go purely mathematical problem. So let's say I d theta. And Cauchy was trying to transform this into complex integration. So he said c equals exponential I theta. Then dz exponential I theta, I d theta, over d theta is I exponential I theta over dz is I z dz. Z plus 1 over z is exponential I theta plus exponential minus I theta is 2 cosine theta, right? So, therefore, cosine theta can be defined as 1 over 2 z plus 1 over z. And this integration can be changed into unit circle C. So I becomes C IZ dz A plus 1 over 2 C plus Z P. So Cauchy transformed this theta integral into this complex integral. C is a unit circle. So 1 over I dz az plus b over 2 z square plus 1 becomes 2 over I dz b square z square plus 2az plus b. Becomes 2 over IB C, not B square, just B, Z square plus 2A over B plus 1 dz, right? So Cauchy transformed this integral. Oops. What happens? I didn't do anything. So he transformed the original integral into this complex integral. So I becomes, I don't know what happened to this. Maybe 2 IB C Z square plus 2A over B Z plus 1 dz, right? Let's try to factorize. So Z square 0 minus A over B plus minus A over B square minus 1, right? So let's assume that A is equal. So for A greater than B, let's say Z1 is minus A over B plus square root of A over B square minus 1. Z2 is minus A over B minus A over B square minus 1. Let's assume that both are greater than 0. Then we have the following. Maybe somewhere here. Right? This is C. So c squared plus 2a over b c plus 1 is c minus c1, c minus c2. Correct? That's from your middle school days. Parabolic equation, 2차 방정식. How do we factorize? How do we do fractional expansion, 부분분수분해? Plus, right? So how do you determine A and B? The simplest way is for A, right? Then what happens? 1 over c minus c2 is A plus c minus c2 over b over c minus c1. Set z equal to z1 means A is c1 minus c2 over 1. Right? B probably learned that you're middle school or high school, right? How to do that, the partial fraction expansion, 부분분수 분해. You multiply c minus c2 and set c equal to z2. Then the left-hand side becomes 1 over z minus c1 is A over c minus c1, 2 plus b. And if you set z equal to z2, b is c2 minus c1. Therefore, b is g2 minus, g1 minus g2. Right. A is 1 over g1 minus g2, b is g2 minus g1. Right? Let me double check. G1 minus G2. Let me double check the coefficient. So G1 minus G2 over that, right? So I becomes 2 over IB C C1 minus C1 C minus C2 over DZ becomes 2 over IB C1 minus C2 over C minus C1 C minus C2 over DZ. And if my memory serves, C1 was minus A over B minus or plus C2 was minus A over B minus A over B square minus 1. So Z1 minus C2, Z1 minus C2 is actually, if you subtract this from this, subtract this Z2 from Z1, we have twice of the square root, right? So twice of A over B square minus 1. Wow. And we know that the unit circle includes only 1. So we know that this circle Z minus C1 over dz is 2 pi I. C minus C2 over dz is 0. Oops. Right? According to Cauchy's integral theorem and the previous result, if you integrate this C2 is outside of this, right? Point Z2 is outside of this circle. So therefore, you should be 0, right? And Z1 is inside, and we have a previous formula that is 2 pi I. So, so we have I, right? 2 over IB and 2 over square root of A over B square minus 1 over 2 pi I. So this I cancels each other, these 2 cancels each other, and it becomes pi over B A over B square minus 1 equal 2 pi B A square minus B square root. So Cauchy obtained So actually, we don't need to have this final form. Provide A is greater than B, then I guess you know how to program C or C plus? The problem, try to numerically integrate. Homework. You don't have to turn in, just for your own benefit. Try to integrate I numerically for various A greater than B. 한번 집에서 컴퓨터 프로그램을 짜가지고 수치적으로 한번 접근을 해보고 A가 B보다 큰 경우는 컴페어 리뷰나 아날리티컬 낼 필요는 없어요. 재미있는 문제가 될 것 같아요. 한 10줄 쓰면 되나? 매틀랩 같은 것도 있잖아. 매틀랩 actually they have I think integration routine. You just call the function. Or Mathematica. Or you can just program it. Summation. It could be a very interesting problem. General case. Sorry. series. His name. Lorentz Kupsu. Then this is it. A0, B0, anyway. As what happens this function? When z is approaching z0, what happens to this function? It becomes infinite, right? Before the first term. Fc becomes infinite. And when Pm is non-zero, we say call Fc as a pole of order m. And what happens if we integrate this? If we integrate this across curve, all the terms become zero, right? Except this one. Two pi I p minus one, right? 왜냐하면 because we know that two pi I delta m minus one, right? We have shown this previously. So even though this function has many other terms, when you integrate, only this term survives. So this is called residue. This coefficient is called residue. So that's also one of the beauty of a complex integration, that even if the function is very complicated, when you integrate, you only need to know one coefficient is. Right? Right. So if you have a very complicated expansion of this function, but when you integrate, you only need to know this one. That's actually the merit of doing complex integration. So Cauchy knew that no matter how the function is complicated, if you can expand this function in terms of this form, then you only need one coefficient to this integration. This is a residue. let's go back to this FC. etc. So now the question is how to find B minus P1. The question, how to find this coefficient or residue. So let's just try. What do you have? PM and then you differentiate with the n times, n plus 1, n minus 1 times. What do you have? If we differentiate this by z n minus 1 times, all the previous term will go to 0, right? And the first term will be m minus 1 factorial, p minus 1 plus, etc., etc. And these terms will goes to 0 as z goes to z dot, right? There are other terms like z minus z naught and square and etc., etc. But if you set the limit that z goes to 0, then the other terms will go to 0 too, right? So therefore, as z minus z naught dz d m minus 1 z minus z naught to the m fc is m minus 1 factorial p minus 1. So that's the formula that how to calculate this residue. So therefore, for a pole of order m, b minus 1, c goes to 0, c naught 1 over m minus 1 factorial, dz d to the m minus 1, c minus c naught to the m fc. So how do we find the order then? If infinite, but is finite, then you say it's pole of order 1, right? In this case, or sometimes we call it simple pole. Pole of order 1 is called simple. If limit goes to 0, fc is infinite, but is finite, then we say this is a pole of order 2. So let's do some example. Or maybe 3, 4, etc., right? And sometimes this is called residue. At C naught. It's called residue. So let's do some example. We need time to copy. Oh, so find the location of pole and order. You have pole at
So has 4 at c equal to 1, right? Order? Order is equal to simple 1, right? How many poles does it have? This function is 2 poles, right? One is equal to 1, and another one is equal to 2. How about order? One is 1, the other one is 2. Right. Poles. This function has poles at c equal to 1, order 1, right? C equal to 2, order 2. Plus fc, z minus 1, z minus 2 square, z minus 3 cube. So for this problem, how many poles this function has? 1, 2, 3, right? How about order? 1, 2, 3. So it has 3 poles. At 1 z equals 2, z equals 3, with order 1, 2, 3, right? How about this function? This is a little bit more complicated. Sine z over 1. How many poles does it have? Z equals 0 is this pole, right? But also anti. So it does have an infinite number of poles. How about order? Right? Pi minus pi, 2 pi minus 2 pi, etc., etc. So if you infinite number of poles. How about order? Is equal to, according to L'Hopital theorem, 1. Right? So it does have a simple pole. Another problem, sine z. Next problem is a little bit more intriguing. That a missing page. I don't know how to delete this. And this previous page about L'Hopital theorem. If let's try to do it for real case. Fx is 0, Gz is 0. Then L'Hopital theorem says prime x equal to x0 is fx over gx, same as f prime x0, g prime x0.
You probably learned that your high school days from memorized.
So actually this can be written as this. Delta goes to 0, fx0 plus delta, gx0 plus delta, right? And minus, you can do this.
So this is, so we change x by x0 plus delta. Then this is already 0, right? This is already 0.
And we divide by delta, right?
You divide by delta and multiply by delta is the same as just 1.
Then it's obvious. G prime x0, f prime x0.
So we can utilize one empty page.
So L'Hopital theorem is very useful theorem, so you probably need to memorize this. Let me see. I think I'm going a little bit fast and probably you must be hungry. How about stopping here today? All right?
We have a real case, exponential x is never less than 0, right? So it's 1 over 1 plus exponential x does not have a 4. How about complex case? When z I pi, what happens? I pi. Exponential I pi and minus 1. It does occur as I pi minus I pi. So infinite number of poles actually.
Poles at plus minus I pi, 3 pi, etc., right? Order, we can try. We can also apply L'Hopital theorem. Exponential z, 1. is finite. Sorry. Anyway, so this has become finite. So simple pole, right? Order of 1. Maybe I can use